Welcome to Lecture 29. Today we're going to be talking about time-dependent perturbation theory. This is one of the most important topics in quantum mechanics because it tells us how states make transitions from one state to another state. And indeed, this is really where quantum mechanics first started. If you think about the spectroscopy that comes from light emitted by atoms, it was known even as early as the 1880s that light and atoms had spectral lines come out of them when they were excited to higher energies, and the light came out with very definite frequencies. And the whole theory of quantum mechanics was developed to try to understand where and how and why these very sharp frequencies occurred. And the way in which we do it is via time-dependent perturbation theory. We'll understand how we make transitions from one state to another. So we're going to begin with our general interaction picture formalism. As you recall, what we did was we wrote the Schrodinger wave function as a time evolution operator, but we factored out the exponential that corresponds to the time evolution with respect to the h0. Remember, h0 is the time-independent part of the Hamiltonian. That's a factor e to the minus I over h bar h0 hat multiplied by t minus t0. Don't confuse yourself. That's not an argument of the Hamiltonian. That's a number that's multiplying the Hamiltonian operator. And then it has a U interaction picture that evolves me from t0 to t of the initial Schrodinger wave function psi s at t0. And the interaction representation time evolution operator was a time-ordered product of the interacting potential, and it's written as the time-ordered product e to the minus I over h bar integral from t0 to t, v interacting of t prime, dt prime, and we could expand that in a power series of the potential v because it acts just like an exponential, and we get terms that look like 1 minus I over h bar integral from t0 to t, vi of t prime, dt prime, plus minus I over h bar squared integral from t0 to t dt1. That second integral should be an integral from t0 to t1 dt2, and then we'd have a vi of t1, vi of t2, and notice that as long as that second integral only goes to t1, there's a typo in the notes, the earliest time is to the right, or as I gave you to remember this before, later times are on the left. Okay, so we can just substitute that in. That will tell us what psi of t is, and if we're interested in what is the probability to have a transition from some initial state I to some final state f, it will simply be the modulus squared of the overlap of the final state with whatever the wave function is at time t. And we can write that in the following way. The probability to go from the initial state to the final state at time t is the modulus squared of the overlap, or the matrix element, between the final state and the time-evolved initial state at time t, which is written as e to the minus I over h bar h0, t minus t0, u interaction of t0 acting on the initial state, that whole thing modulus squared. Now, if the initial and final states are eigenstates of h0, then we can operate the h0 to the left acting on state f. It becomes e to the minus I over h bar ef times t minus t0 times the state f. That's just a phase factor. The norm of the phase factor is 1, and so that term will actually disappear from the expression, and we'll be left with the transition from an eigenstate of h0 called m to an eigenstate of h0 called n will be given by the modulus of the overlap of m with the interaction evolution operator acting on the state m overlapped with the state n. And because we can write that in a power series, we immediately have our perturbation theory expression as a power series in the potential v. Now the first term, because the states n and m are orthonormal, is given by delta nm, and then the next state, the linear state, is minus I over h bar overlap of n with the integral from t0 to t, e to the I over h bar h0 t1 minus t0, v of t, e to the minus I over h bar h0 t minus t0 acting on the state m0. Because, again, those states m and n are eigenstates of the time-independent piece of the Hamiltonian, h0, we can re-express those in terms of En and Em. We define the frequency omega nm to be E0n minus E0m divided by h bar. And what we find is that the lowest order approximation, if we just include that lowest order term in the perturbation theory, our first term is going to be a delta nm. We're going to get a minus I over h bar integral from t0 to t e to the I omega nm of t1 minus t0. And then this matrix element 0 n v hat of t1, 0m, and then we integrate that all with respect to t1, so we have a dt1. Then we have to take the modulus squared of that entire expression. Before, we used a notation to represent the matrix element n0 vm. We call that vnm of t1. That's a matrix element. It's no longer an operator. And we have our expression for the probability. Now, one of the things we're most interested in calculating such a probability is what is the probability to make a transition from one state to another state. So if it's true that my final state is not equal to the initial state, I'm not calculating the probability to stay in the state, I'm only calculating the probability to make a transition to the next state, then the lowest order expression will be 1 over h bar squared, integral from t0 to t dt1, e to the I omega nm of t multiplied by t1 minus t0, the matrix element vnm of t1. All of the time dependence in vnm comes from the time dependence in the operator. This is not the operator in the interaction picture. This is the operator in the Schrodinger picture. Okay, so it's that easy. That's how we got the lowest order contribution for this transition between state m and state n in the case where n does not equal m. Now, there's a very important approximation or case that we would like to look at. It's actually not an approximation. It's a very important case of a perturbation, which is called a harmonic perturbation. And that's when the operator in the Schrodinger picture, v of t, can be written as the sum of an operator and its Hermitian conjugate. In this case, we're writing it in terms of some operator little a dagger. When we talked about the simple harmonic oscillator, that was the lowering and raising operator, but now we just are going to think of that as any old operator. And so a harmonic perturbation is just e to the I capital omega t a hat dagger plus e to the minus I omega t a hat, and you can immediately see that that's a Hermitian operator, but it's a Hermitian operator that is the sum of the Hermitian conjugates of two terms. And we're going to pick omega to be greater than 0. We're going to call that the driving frequency. Now, because we need the matrix element of V in these states n and m, we're going to assume that we have two states n and m where n overlapped with a hat m is not equal to 0, so that matrix element is non-zero, and we're going to take t0 equal to 0 for simplicity in our formulas. Then what we find is the probability to go from m to n when n is not equal to m as a function of time is 1 over h bar squared integral from 0 to t dt1 e to the I omega nm t1 multiplied by a nm e to the minus I omega t1 plus a nm star e to the I omega t1. And we take the whole modulus of that thing squared. But notice, because of the way we chose this harmonic perturbation, where we put an explicit time dependence for this harmonic perturbation in terms of an exponential, we can actually now do the integral. So the integral is very straightforward to do. It's just the integral of an exponential. I'll get 1 over the exponent, and I'll get the exponential evaluated at time t minus the exponential evaluated at time 0. When we work that out for these two cases, we'll get 1 over h bar squared, the modulus squared of a nm over I omega nm minus big omega, e to the I omega nm minus big omega times t minus 1, plus a nm star I over omega nm plus big omega e to the I omega nm plus omega times t minus 1, that whole quantity, and then the sum of those two terms modulus squared. So we can go ahead and work out what the different terms are. We're going to get terms that involve the overlap, the modulus squared of this, so I have to multiply it by its complex conjugate. And what we find is we get a number of different terms. 1 over h bar squared a nm modulus squared over omega nm minus big omega quantity squared times 2 times 1 minus cosine omega nm minus big omega times t. That's what we get when we multiply the first term multiplied by its complex conjugate. you should be able to see that that's exactly what comes out. Now the second term in the sum is coming from the second term multiplied by its complex conjugate, and that will be a ANM over omega NM plus big omega quantity squared, 2 times 1 minus cosine omega NM plus big omega times t, plus the remaining terms which involve the cross terms when the ANM multiplies the complex conjugate of the second term. That will involve an ANM squared, and there'll also be a term that involves an ANM star squared. In both cases, that's not the modulus, but the sum of those two terms, because they're complex conjugates of each other, will be a real term. We're going to just call those cross terms at the moment because we're not going to be worried about them. The terms that we've already included are the terms that are going to be giving the dominant contributions when the driving frequency is close to one of these energy differences. So if we collect up our terms, we see that we can rewrite this as 4 over h bar squared, the modulus of ANM squared, multiplied by sine squared omega NM minus omega times t over 2. We used a trig identity there to replace the 1 minus cosine omega NM minus big omega times t with a sine of a half angle formula. It's divided by omega NM minus big omega quantity squared. And then we have the sum of a similar term that we're going to get from the other term that has the ANM modulus squared in front of it. Its denominator will be omega NM plus big omega squared. Now, these two terms, and then of course there are cross terms that are added as well. We're ignoring them for the moment. Now the first two terms, the first one will be very large when omega NM is bigger than 0 and it's approximately equal to big omega. The second term will be large if omega NM is less than 0 and omega NM is approximately equal to minus big omega. Both of those conditions, when the denominator is very close to 0, are called resonance. And we expect that when we're on resonance, we're going to get a large contribution or a high rate of transitions because we're driving it at the natural frequency that the system can be driven at. Now, when omega NM is equal to big omega, so that's when omega NM is positive, that's when the first term on the previous page is large, what we can find is that En will equal Em plus h bar omega. That's a process called stimulated absorption. En is bigger than Em. We're bringing a photon in or some energy in, and the system is absorbing that energy, and it is making a transition from the lower energy state M to the higher energy state N. In the other case, when minus omega Nm is approximately equal to big omega, that's the case when En is equal to Em minus h bar omega. That's a process called stimulated emission. That's when we're going from a higher energy state to a lower energy state, and that transition where I go from high energy to lower energy is being stimulated by the fact that I have some excitation that is coming in at a frequency of big omega. So you can schematically think of that as a photon coming in and stimulating a transition from a high energy state to a low energy state. This is a process that's very important for lasers. All right, this is a perturbation theory, so let's talk a little bit about accuracy. This approximation where we only include the first non-trivial term in the exponential when we do the expansion of the exponential, that's called the first Born approximation, and in order for it to be accurate, we need these transition probabilities to be much less than 1. The worst case for that, of course, is when we're on resonance, because then the transition from M to N, if we look at that expression, will go like the square of time multiplied by some constant, and that's going to rapidly become larger than 1. Now, in general, if we had an exact solution, we would find that the probabilities will oscillate with time. And to keep you grounded, I ask you to remember what happened with the cyclotron resonance problem. In the cyclotron resonance problem, we had a situation where our transition frequencies were cosines or sines, and we had this oscillatory behavior and oscillatory dependence. So the problem with first-order perturbation theory, in addition to the fact that it will generically not always give us this oscillating behavior, is that it neglects two important physical properties. One is called depletion, the other is called return. Depletion means that we expect the probability of making a transition from M to N to decrease as we deplete the system from many states that are occupied with the state M. If all of those states are gone, I can't make the transition from M to something else. And this first-order perturbation theory doesn't take that into account. The other thing is called return, which says after I've populated a large number of N's, they're going to undergo this stimulated emission and re-emit the energy and go back to the state M. And both of those processes are higher order effects. So for example, if you consider something like the photoionization of hydrogen, that's when a photon knocks an electron out of hydrogen, there's actually very little chance that the electron will return back. That's because it's given enough energy, it moves away from the atom. It won't be able to find the atom, be close enough to it to come back. And so in that case, neglecting the return process would be actually a pretty good approximation, even on physical grounds. All right, so we've worked out this detailed expression of time-dependent perturbation theory. We also have an exactly solvable example that we worked on from the last lecture with the driven harmonic oscillator. Let's take a look and compare what the two results give. Okay, so you need to recall from last time we showed that the Schrodinger wave function could be expressed as this operator expression. Our first term was e to the I omega t a dagger a plus a half. That's just the h0 term. And then we had this operator expression that involves a sum in the exponent of an a dagger and an a term. And then we have this final term, which is just a function, has no operators in it. And all of that is acting on the state psi s of 0. And just to remind you again, the h0 is the simple harmonic oscillator, h bar omega a dagger a plus a half, plus some constant times e to the I omega t a dagger plus another the same constant, which is real, times e to the minus I omega t times a. And recall once again that in this particular case, the a really is a lowering operator and the a dagger really is a raising operator of the simple harmonic oscillator. This is a harmonic perturbation as well. Okay? Now, we know how to handle this term that has the exponent of the a dagger and the a. We use this BCH identity. It's quickly derived for you here, but we really derived this earlier in the class. I will let you take a look at the notes to look at the derivation again. But what we know is that e to the a plus b is equal to 1/2 the commutator of b with a multiplied by e to the a and e to the b, and this holds whenever the commutator of b with a is a number, not an operator. If you want to see the way that you can derive this by looking at a differential equation, it's very similar to the kinds of differential equation work we did earlier in some earlier lectures, but as we mentioned before, we've already derived this expression earlier in the class. You can go back and take a look at how we did it there. You can take the time to read the notes here. I'm not going to go over it in detail because we know the result. We're simply now going to use it. Okay, so we're going to apply that to a equals minus c over h bar big omega plus little omega multiplied by e to the I little omega plus big omega t minus 1 a dagger, and b is equal to c over h bar little omega plus big omega multiplied by e to the minus I little omega plus big omega t minus 1 multiplied by a. The commutator of b with a, we're going to just get the commutator of a with a dagger. That commutator is 1, and then we're going to just get the product of both those terms. It gives us minus c squared over h bar squared little omega plus big omega quantity squared times 2 times 1 minus cosine little omega plus big omega times t. So if we start in the ground state, now this calculation we're doing here is exact. We will find that the probability to go from 0 to state m as a function of t, where 0 is the ground state and m is some excited state of the simple harmonic oscillator, will have a term that goes like e to the I omega t a dagger a plus a half. That operator can immediately act on the m state. It will just give a phase, and when I take the modulus squared of that, I just get 1, so we can ignore that term. Then we're going to get these two terms that we worked out, e to the minus c over h bar omega, little omega plus big omega, e to the I little omega plus big omega t minus 1 times a dagger. And then we're going to get this term e to the c over h bar little omega plus big omega e to the minus I little omega plus big omega t minus 1a acting on the vacuum state or the ground state 0. And then we're going to get the collection of all the other functional terms, and we're going to take the modulus squared of those functional terms. I'm not going to read those out to you. They're written right for you here. We can collect those together and we can bring them out of the expression. One of the terms has an I multiplying it. That's going to just give a phase. That term's going to disappear. The other term, when I take the modulus squared, since it's real, is just going to get a 2 in front of it, so that's going to get factored out. The e to the exponential of the a operator acting on the ground state, that just gives 1. We've seen this identity before. You just do a power series expansion, and using the fact that the a operator annihilates the ground state tells you that all the higher order terms after 1 are equal to 0, so that expression can be replaced by 1. And then the term with the exponential of the a dagger, well, that's going to just be a polynomial in a dagger. Now, if I operate it with an m state on the other side, I'm going to move the paper up just a bit so we can catch up here. If I operate that with an m state on the other side, the m state is a raised to the mth power over the square root of m factorial. So it's going to only pick out one of the terms in that polynomial expansion of the exponential. So when I do the Taylor series expansion of the exponential, only the term when n equals m is going to contribute. And you see, when I look at the expectation value of a to the m with a dagger to the m, that expectation value is just equal to m factorial. That'll cancel the 1 over m factorial. I'm still left with a 1 over square root of m factorial. And I'm left with some constants. This minus c over h bar little omega plus big omega, and this exponential factor e to the I little omega plus big omega t minus 1, that whole thing raised to the mth power. We're now going to do a squaring of that. I'll get a 1 over m factorial from the square root of m factorial. I have done a squaring of that term, so I have a c squared over h bar squared little omega plus big omega quantity squared. And then when we look at the modulus squared of e to the I little omega plus big omega t minus 1, that's equal to 2 times 1 minus cosine little omega plus big omega times t. And so that whole thing will be raised to the mth power. And now we have to just collect coefficients and collect terms. And what we get is this probability is going to be 1 over m factorial, 2c squared over h bar squared little omega plus big omega squared raised to the mth power, 1 minus cosine little omega plus big omega t raised to the mth power, and then we have this exponential factor e to the minus 2c squared over h bar squared little omega plus big omega squared, 1 minus cosine little omega plus big omega times t. This is exact. And it actually wasn't all that hard to calculate. The hard work was working out that exact time-ordered product expression from the previous lecture. Once we had that, we just needed to do a little bit of BCH and a little bit of the knowledge of what the ground and excited states of the simple harmonic oscillator were, and boom, we get the answer. And there it is. So that's pretty impressive. This is an exact expression. Now, in order to check accuracy, we want to compare that expression to the result that we would get for the time-dependent perturbation theory. But before we do that, we can easily check that if we sum this over all m, we're summing the square of the probability, you can immediately see that if I express the probability as the complex conjugate of one matrix element times the matrix element, and I do a sum over m, I'm going to get a sum over ket m bra m in the center, and we can replace that with 1, and we'll get the square of the time-dependent Schrodinger wave function at a given time, and we know that the norm of the wave function is preserved, so that square is equal to 1. We can, however, just take our result here that we got for a particular m, this probability, and we can sum it over all m, and what you find when you sum it over all m is that expression that depends on m, that's the Taylor series expansion for an exponential. So you immediately get that that term is an exponential of a plus 2c squared over h bar squared little omega plus big omega squared 1 minus cosine little omega plus big omega times t. And that's exactly the opposite of the term we already had. And so when I add those two terms together, the exponent goes to 0, and the whole thing is equal to exponential of 0 or 1 as it must be. So that's a very nice check that we didn't make a mistake in our algebra or in our derivation. All right, let's compare this to the harmonic calculation. In the harmonic calculation, what we get is we have to look at the overlap of state m with the harmonic perturbation. There's only one state that's going to have a non-zero overlap because the harmonic perturbation has a single raising operator. And it's going to equal c times delta m1. Now, omega 1, 0 is just equal to omega. That's the energy it takes to excite myself from the ground state to the first excited state. So we plug into our time-dependent perturbation theory formula, and I strongly recommend you do that, and you'll get 4c squared over h bar squared sine squared little omega plus big omega times t times a half over little omega plus big omega squared. And this agrees exactly with the form that we have above for m equals 1 when we do a lowest order expansion in c squared. Okay, so let me take you back here. Let's take a look at this. We have to first set m equals 1. And then I have to expand that exponential as a power series in c squared. And we only take the lowest order term, which means replace the exponential by 1. And so you see what we're going to get is that this is 2c squared over h bar squared little omega plus big omega squared times 1 minus cosine little omega plus big omega times t. So now if we come back and we use the fact that 1 minus cosine little omega plus big omega times t is 2 sine squared little omega plus big omega t over 2, that's just a trig half angle formula, you see that these two expressions agree to order c squared. And of course they had to, because we're doing a time-dependent perturbation theory and we had an exact solution. If we expand that exact solution to the same order as the perturbation theory was performed, we have to get the exact same answer. So this is a nice way of using our exact result to check to verify that our perturbation theory is working properly. And now we have two ways that we can attempt to solve problems. If we have a way of properly determining the time-ordered product, we can of course just solve the problem exactly. If we're not so lucky and we cannot work out what the time-ordered product is, then we can do this perturbation theory and at least determine what the results are order by order in the perturbation series. Of course, we only did this to first order, and for most problems that you look at in time-dependent perturbation theory, first order is all anyone ever does. Okay, that's all for Lecture 29. We'll be back with Lecture 30 the next time.